so a couple of weeks ago, I presented this thing that I called Pail, and one of the outcomes of that was this realization, or like I had a realization that that in like a distributed multiplayer environment, the order of operations kind of matters, like puts and deletes. So I'm going to talk a little bit about why that is, and then I'm going to show you these things called Merkle clocks and CRDTs, and they're things that can kind of address the issue. So for this to work, I'm going to start with our favorite characters in cryptography, Alice, Bob, and Carol. We're going to consider a fruit basket or fruit pail with 3 players, and they are these people. Alice is red, Bob is blue, and Carol is yellow. And what they're going to do is they're all going to add some fruits at approximately the same time to the pail. And we're going to do this from Alice's point of view first. So what Alice sees is like she puts an apple, then she puts a banana, then she sees Bob put a kiwi in, and then she sees Carol put a mango in, and then Bob puts another orange in, or not another orange, or a orange, and then finally she puts this pear in, and that's the order of events that she sees things happen. So, but maybe Bob, due to network latencies, this is where it breaks down a little bit, sees a slightly kind of different order of events. So what he sees is he sees Alice put the apple in first, but then maybe he puts his kiwi in, then he puts his orange in, and then he sees Carol put a mango in, and then he sees Alice put a banana, and then finally he sees Alice put the pear. So the thing is, we end up with the same operations that happened, but they arrived in a different order based on like who you are and what kind of network stuff is going on. And so you can imagine how that might be kind of problematic if any of these players were to be putting or deleting items with conflicting keys. So if 2 of them were putting a key that was like Apple at the same time, then that would be problematic. If someone was deleting something or adding something and then deleting something, what if the delete happened before the add? It would still be there. And if different people are seeing different things at different times, then that's not good, right? So why is this a problem? Why don't we just like put a timestamp on the event and then send that and just sort it by like the timestamp? Well, yeah, like you could do, but like not every player that's playing will have like a perfectly synchronized global clock, for example. It's also easy to spoof, so you could basically just put like a far future timestamp on yours, and then your thing will always happen regardless of whatever everyone else is doing. So that can kind of be problematic in a trustless distributed system, and that's the world we live in, by the way. So here we go. And also, so the big thing is, no, there's no link there. Okay. In Pail, aside from the problem of like key conflicts, we actually can't receive events in a random order for another reason, and that's because the order of applied mutations determine the structure of the DAG in Pail. So we really can't have events going in any old order, even if they don't conflict, because they might end up with a different root CID. And even though like the Pail might contain the same keys and values, it could, if you put them in a different order, then you might get a different root CID in different blocks, etc. And that's not good. Well, not good in a multiplayer distributed environment. So yeah, there's this thing called Merkle clocks, and they make use of the kind of inherent properties of Merkle DAGs, and they basically encode event ordering information. And this paper that Hugo and Pedro and someone else I can't remember, I'm pretty sure I don't know, wrote a while ago.
Hector.
I said Hector.
Hector, you said Hugo.
Oh shit, I mean, not Hugo. Hector, sorry, Hugo.
Hector.
You didn't write this one. Anyway, it's a nice read. It's short and stuff, as papers should be. Anyway, so yeah, that's what I said about that. Right. So how does it work? Let's do it. So basically, each player creates a graph of the events that happen, and they can create events themselves, or they can receive them from other people. And so in this example, we're going to look at Alice's order of events again, and she's just created an event here, and so it's a DAG node, and it's got the CID like ending in H56I. But the operation she's kind of encoded in this DAG node is that she's putting an apple with the value like H, like with that CID. It doesn't really matter what that value is because we're not really considering it for this. But yeah, she's putting an apple for all intents and purposes. She's putting an apple into the basket. Yeah. So anyway, she creates this event, this node in the graph, and she broadcasts that out to other people essentially. And so what happens is that each player keeps track of the kind of latest event that has been created, or they know about, right? And it may be more than one. And it may be more than one in the case where two or more players performed an operation at approximately the same time. We'll see that in a sec. But next up, Alice puts in a banana, like you saw. It's the same thing as earlier. She puts a banana in the bucket, and then she tracks that node as the latest event, and you can see it points back to the first event. So there's a kind of explicit ordering of events here, where obviously the banana was put in after the apple, especially according to Alice. And then like soon after, what happens is she receives an event from Bob, and Bob's put a kiwi, and what happened, because Bob's kiwi points to Alice's apple, we can kind of derive from this that at the time that Bob created his kiwi, he hadn't received the event from Alice to say that she'd put a banana in, and that's okay. And this is where the keeping track of multiple events comes in. She's now Alice keeps track of like these two events as the latest event that happened. So she's keeping track of the banana and the kiwi. Yeah. Cool. So then Alice receives an event saying Carol's put a mango in, and Carol's message also doesn't point to Alice's banana. So she knows that Carol hadn't received Alice's banana at the time that she put the mango, but she had received Bob's kiwi message or event. And so Alice's two latest events have been updated now, because the mango has, by virtue of it linking to the kiwi, come after the kiwi. She's now pointing to two events. And then okay, she received another event from Bob. He put in an orange, unbelievably crazy set of events here. It's before he knew about the banana or the mango from Carol. So madness ensues, but it works out, don't worry. It's because his orange now points back to his kiwi, and he's broadcasted that event out, and everyone's got that event, so they can build this graph up. So that's fine. And Alice is now tracking three latest events: the banana, the orange, and the mango. Cool. And then so finally, this is the last thing that happens in the set of events that we're considering here, is that Alice adds her third item, which is the pair. The pair actually links to these three other events, because Alice has received the orange, the mango, and the kiwi from these other participants, and they were the three things that she was tracking as the latest event. So now when she puts another event in, her new event links to all three of them, and so this is where we kind of converge. And so what you'll kind of notice is that whatever order that we receive these events in will still like create the same graph. And you can even like miss events entirely. So Alice could just not get the event from basically if Carol's mango doesn't get broadcasted to Bob at all, but he does receive the pair, he'll find out about the mango just by virtue of the fact that it links to the mango, even if he can't reach her over the network, essentially. Cool, so that's kind of fun. So what can we kind of say about the order of the events that happened here? Well, we know for sure that the apple was added first, and the pair was added right at the end. We can see that because of the way the graph is. We can also say like the banana was added around the same time as the kiwi and the orange and mango, but we don't know if it was added like before all of that or after all of that or somewhere in the middle. Like we just don't have that information encoded in this graph. And so it was, but what we can say is that the banana was definitely added after the apple and before the pear. And then about the orange and mango, we can say that they both came after the kiwi, but we don't know like if the orange was added before the mango or the mango was added before the orange. But we know some information about it basically. And then so finally we know that the kiwi came after the apple for sure, and the pear came after the orange and the mango, although like I said, we don't know which order the orange and mango came in. So all right, order. Do we have an order of events from that? Well, kind of no. We have a bunch of unknowns. We can say some things about the graph in terms of the ordering. So how do we actually resolve the order of events like completely unambiguously? Well, what we can do, one way of doing it, at least, this is kind of the way that I've done it for jokes. We can actually weight the nodes. So you can kind of traverse the graph, and as you traverse the graph, you can assign a kind of depth for each node. So from the root, if we go pear, banana, apple, we go depth 0, 1, 2, and then so pear, orange, kiwi, apple would be 0, 1, 2, 3, and then pear, mango, kiwi, apple is 0, 1, 2, 3, and then you can kind of sum up the numbers for each node. So this one will have 3, 6, 8, 8, 1, 2, and then like basically order them by the heaviest first. So you'd end up with something like this. So apple has 8, so that event came first. Kiwi has 4, so that event came next. This one, banana and orange and mango, they all got the weight 1. So we need to figure out like how to resolve this, the ordering of these events. And then pear, obviously the last thing that happened got 0, it doesn't have any weight, and so it's the last thing that happened. Cool. So what do we do here? Well, at least in the thing that I've been messing around with is we can actually order by the CID of the node of the resulting Pail after putting that event. So when we broadcast events out, so in this graph, this event is basically encodes the operation, the key, the value, but it also has the CID of the Pail that was generated, the root of the Pail that was generated as a result of this operation happening on this person's view of the Pail. So we have a CID, and then what we can do is we can like actually just alphabetically order those CIDs and get a kind of an ordering that is consistent across all nodes without them having to basically converse or come to consensus. That's the word I'm looking for. Cool. So that's what I do. But like you could also, like, for the events, actually add a timestamp, and in this case where you do have conflicts like this, you could then use the timestamp perhaps, or maybe there's some other way, or something else you could do. I don't know. I've literally just learned about these things and built something that's kind of interesting. So what I was thinking next is I basically want multiplayer Pail, but what I wanted to build was like this kind of you can service where you can delegate people the ability to add to the Pail. But then I realized actually you don't need to delegate explicitly to the Pail. You can delegate the ability to change the clock, and if you can change the clock, then that's the same thing as sort of changing the Pail, and then you can actually use that for any kind of a CRDTE thing that you want to build. It doesn't have to be Pail, it could be any kind of application. And if we could build Merkle clock as a service, or MCAS as I like to affectionately refer to it, then we could do something like this. Maybe like you could delegate a UCAN, which allows people to advance the clock by one event with the, like maybe the clock has a DID, obviously, and then the event is just a CID of the block that encodes the event information. And then, I don't know, we kind of need a way of like being able to receive broadcasted events, like, I don't know, IPFS PubSub, maybe a WebSocket in our world, Web2 style, don't know, something like that. And then you sort of also need like the how do I bootstrap thing, which is kind of what is the current state of the world, and being able to fetch a head from one of the players in the participating would be useful. So you could maybe also delegate them the ability to fetch the head from someone. And then what I was thinking is that actually web3.storage could be just one of those players, and then they're just like the always online player where everyone else can just go away. And web3.storage could, you know, this could be what Merkle clock as a service is. It actually stores the current head at any given point in time. Anyway, that's my presentation.